excited to have Steffen here with us. I cannot see Steffen video. Maybe Steffen, can you turn on your audio so that I can see you?
Sorry, can I turn on what?
Yeah, okay. All right, I can see you now. Okay.
Okay.
So yes, so Steffen is from Department of Mathematics and Statistics at Lancaster University, England, and he works on a lot of different topics in non-parametric statistics. But I know mostly him from his work on multi-arm bandits. I also have the pleasure of co-authoring a paper with him on delayed feedback, which was a lot of fun. And so today he's going to talk about multitask optimal experiment design. Take it away.
Thank you, Shipra. So this is joint work with Maya Fazel from University of Washington. I should say this is all preliminary work, so we don't have anything on arXiv yet or published, but I think the framework I discussed is quite interesting, the setting, and I'll point out a few which I find surprising results. So let's get to the setting. If I know how to change slides, okay. So generally I'm dealing here with a high dimensional Hilbert space H, finite dimensional but high dimensional, just to have enough degrees of freedom to put a multitask setting in. So essentially I'm dealing with multiple settings in which I try to infer a parameter theta I, and I play multiple rounds, and a high dimensional Hilbert space is pretty good to model the setting. Generally, I have some parameter theta null in this high dimensional space, which is unknown, which I essentially try to infer from data. I have a simple observation model. I might sample a point H, A in H, and get an observation which corresponds to the usual inner product between A and theta null. So the mean of the distribution and some noise term, which for simplicity I'll assume here is a standard normal random variable, but anything that is essentially zero mean and has reasonably nice properties would do. So pretty much standard least square setting, if you like, nothing particularly fancy here. Now I'm interested in turning this into a multitask setting. So I'm interested in having multiple epochs, which I will enumerate with I. So I'm running from I equal 1, 2, 3, and so on. In each epoch, I get a set of actions or design points from which I can sample, which I will generally note with AI. All of these design points are obviously living in the Hilbert space. And these design points change from epoch to epoch. In each epoch, I can have multiple rounds in which I'm allowed to sample from these design points. But between epochs, my design points change. Goal is generally to estimate the function which corresponds to the mean. So I'm interested in estimating f of a, where this function f is simply the corresponding to the inner product between a and theta null in our Hilbert space. So there's now two variations of the problems that make sense. Either I'm only interested in estimating my function at my design points ai, or I'm interested in estimating the function over the whole span of AI, which I will denote in the following with UI. So either I'm interested in getting a good estimate for the whole subspace, or I'm only interested in the design points. So this is obviously quite closely related, pretty much the same as trying to estimate the projection of theta null onto the subspace UI. I will call this projection the projection operator, generally here with PI. So these are orthogonal projections onto the subspace UI. And the parameter that corresponds to my design point set in epoch I will be denoted with theta I. So this is simply the orthogonal projection of my big theta null onto my potentially small subspace, which corresponds to my current epoch. Then obviously we have here that's the inner product between A and theta null. If A is a design point in epoch I, is the same as the inner product between A and the orthogonal projection of theta null onto UI, which is the same as the inner product between A and theta I. So that's the quantity I care about in epoch I. So I have some figures here, unfortunately not very nicely done with ticks. So this is all iPad drawing. I hope it still explains the point. So we have our high-dimensional Hilbert space. Here I depict 3 dimensions. We have somewhere an unknown parameter theta null. Then as the game proceeds, I'll get a set of design points, AI, and a corresponding subspace. Say for simplicity, my first subspace is U1. So I have a one-dimensional space in which I have certain design points from which I can sample. Say in epoch 2, I get get design points which will essentially span the space U2. So the green area here, 2-dimensional subspace, corresponds to my space which I care about in epoch 2. And I have the orthogonal projections. So this is not really orthogonal, but it's meant to be an orthogonal projection of theta null onto U1, which corresponds to parameter theta 1, which is the parameter I deal with in epoch 1. Then in epoch 2, I have the orthogonal projection of theta null onto that subspace corresponding to theta 2. So the idea is now multitask setting makes only sense if there's some information shared between the different tasks, if there's some information you can use from previous tasks to inform your decisions in new tasks. Here, essentially, the information can potentially be passed between the tasks if the subspace U1 is in some way close to the subspace U2. So if you think of, for instance, two-dimensional subspaces, or say 2 one-dimensional subspaces, and if you have a small angle between these subspaces, then if you sampled a lot of points in this subspace in epoch 1, then you will hope that this information will help you in the new epoch, simply because both share the same parameter theta null. So there should be some information passing between the epochs, in particular if the subspaces are in some way closely aligned. So if you want a small angle between the subspaces or some other form of distance which is small between the subspaces. So key quantity, obviously, in the setting is some measure of distance between subspaces. There's all sorts of measures to measure distances between subspaces. A quite common way is to compare the orthogonal projections, treat these as operators or matrices, whatever you like, and compare the difference in these orthogonal projections. So P1 here will be my orthogonal projection onto U1, P2 is the orthogonal projection onto the subspace corresponding to epoch 2. And then I can look at the difference between these orthogonal projections and measure the difference in various norms, say the operator norm or the trace norm or the Hilbert-Schmidt norm / Frobenius norm, which all correspond to different geometric properties of the subspaces and measure differences in different forms. So in this talk, I'll pretty much just focus on the operator norm for simplicity. This essentially is saying that you fix a point in subspace U1 in the unit ball in U1 and measure the distance from X to the projection of X onto U2. You take the maximum of that expression with the corresponding expression for having a point in U2, and that is giving you the operator norm between P1 minus P2, which corresponds to some kind of similarity measure between the corresponding subspaces and the corresponding epochs. So in the setting, there's obviously various interesting questions that you can ask. Actually, I find the setting quite complex, and I find it more challenging to figure out which is the right question to ask. So a lack of questions doesn't seem to be a problem in this context. So I guess the most natural question is, how much can an estimator for theta 2 profit from samples in U1 independence of the distance between the subspaces? So generally, I will use here capital theta U1, U2 to describe the distance between the subspaces. So here is the distance in operator norm between the orthogonal projections. You might also ask the related question of, can I design somehow my experiments in subspace U1 and U2 in a way that I profit maximally when estimating parameters theta 2. I think in an online setting, it also makes a lot of sense that you would have a greedy algorithm, which, for instance, in epoch 1 optimizes the estimate of theta 1 without caring about future epochs. The question you can ask then is, how can a method in epoch 2 profit from these samples, which are not necessarily designed to support your estimation in the second epoch? Finally, you can obviously go beyond 2 epochs, have a whole sequence of epochs, a whole sequence of design points and corresponding subspaces, potentially with a whole sequence of distances between these subspaces. And you can ask, what is my performance in epoch n if I have a sequence of distances between subspaces given, and I guess corresponding numbers of samples in these subspaces. So there's a variety of questions that you can ask. I'll focus here on the simplest possible question, that is question 1 and 2. I will measure the difference between the settings using the operator norm, and I have two epochs, 1 and 2, with corresponding subspaces U1 and U2, and I'm interested in estimating θ2. My Hilbert space, for some part, will, for simplicity, simply be the span of U1, U2, so not that large dimensional, that high dimensional, but the propositions I'll state work for the more general case where you have a high dimensional Hilbert space.
Steffen,
was there a question, or is that?
Yeah, like quick question. So I guess based on what you just said about that the Hilbert space is the span of both of these operators or whatnot, I assume that U1 and U2 are given in advance.
Yes, yeah.
Because there could be the variation of the problem where you know U1, you don't know U2 yet, and then.
I agree. I mean, absolutely. Further variations for the list, absolutely agree. You might have some, you don't know what happens in the future, which tasks pop up in the future. You might already want to design, put certain points, certain design points to make it easier for future epochs. Yes, absolutely, you can play with that. Okay.
Good, yeah.
Oh, just, okay. Okay, so let's start with a simple estimator. Obviously, I need to have some estimation procedure to discuss this whole idea of profiting from old samples in new epochs. So let's start with something very basic. Just estimate θ null using all data from all the subspaces, from all the epochs, and project it onto the subspace in which you're currently at. Simplest possible estimator, I would say. θ null can be, for instance, θ null hat can, for instance, be the ordinary least squares or maximum likelihood estimator. So that's the one I will use here, of θ null. And then you project this estimator using the orthogonal projection to get an estimate of your parameter θ2. So there's a few properties, standard stats properties, which are directly useful. So there's this invariance property or principle of maximum likelihood estimation, which is saying that if you apply a function to a maximum likelihood estimator, then the result is the maximum likelihood estimator of that parameter that you care about. In this context, what this is saying is that θ hat 2 is the maximum likelihood estimator of θ2. Then you have all these asymptotic efficiency statements for maximum likelihood estimators. In this context, this is saying that θ hat 2 approaches the minimum variance unbiased estimator of θ2 as n goes to infinity. I should mention here, this is when you keep the epochs fixed and let n go to infinity. So I was thinking it might be interesting to make this a bit more interactive. I don't know if the chat is open now.
Yeah, just a quick question. Can I ask?
Okay, can I ask this question and then the question, because I want people, if possible, just
to all right.
Type in A, B, C, D, what's their guesses about these estimators, comparing the estimator just discussed with the ordinarily squares estimators that only uses samples from epoch 2. So if you like to vote in the chat, I would be very happy to get your intuition. And yeah, please, the question. Was there a question?
I was just going to ask to clarify whether the projector operator, the P1, P2, are known to the algorithm? Or?
Yes. So the subspaces and design points are known. So all these things are known. The only unknown is the parameter θ null.
Okay, all right, thanks.
So I don't know, I can't see the chat if anyone actually typed anything, voted or not.
Yeah, everyone can check. I think we need a little more time to read the question.
Okay, so let me quickly explain the four different points.
Yeah,
the question is, the naive estimator could be biased or unbiased. So that's deciding between A, B, and C, D. You would imagine that the variance of the naive estimator improves compared to the estimator which uses only samples from epoch 2. I guess it also might be quite natural to assume that this decrease in variance depends on the distance between the subspaces U1 and U2. So these are pretty much the choices. Variance goes down, estimator is biased, variance goes down, and the decrease depends on the distance between the subspaces. Same too for unbiased. Okay. Anyway, so if you like, type these questions in the chat. I'll answer the first question directly, which is the estimator itself is unbiased. That's quite easy to see. So I'll possibly just quickly go through that line. Theta 2 is the orthogonal projection of theta null. Theta null, because the maximum likelihood estimator for theta null is unbiased, corresponds to the expected value of theta null. Then you can exchange the orthogonal projection with the expectation operator, move the projection inside, and that just simply gives you the expected value of theta null, of theta 2, and the estimator is unbiased. It's also straightforward to get the covariance matrix. C here corresponds to the covariance matrix of the maximum likelihood estimator for theta null. So the covariance matrix is changed through these orthogonal projections, which you multiply on the left and on the right side onto C. Mean squared error, obviously, is then also straightforward, unbiased. We know the covariance, no surprises here. In particular, if I look at an element in subspace U2, because the orthogonal projection applied to an element in U2 just gives back the element. So the mean squared error corresponds to A transpose C minus 1A. So I wanted to, in one slide, to quickly say something about optimal experiment design, which is kind of the topic here. So my design points, I will use finite design points. So in A1, I have little a1 to little a d1, from which I can choose. In A2, I have b1 to b d2. So I will keep this notation for the remaining slides. I can sample points ai mu I times and sample bj lambda j times. So lambda I use for b, mu I use for a. Generally, you have budget constraints, otherwise this whole optimal experiment design is quite boring. So you will have upper bounds on the sum of the mu i's and upper bounds on the lambda j's. I'm not allowing here any passing of budget. So if you don't use budget in epoch 1, you can't use it in epoch 2. Covariance matrix that corresponds to the estimator is simply a weighted sum of the outer products, mu I times the outer product ai, lambda j times the outer product bj. Mean squared error, if I look at a point A, is simply A transposed times the inverse, or here I write the pseudo inverse with a dagger. If the Hilbert space is larger dimensional and I don't have the well-defined inverse, times A. I will also use the notation that this is the norm of A under the C dagger covariance. So just to mention one optimal design, a simple optimal design is G-optimal design, where you try to minimize the worst case mean squared error. In my particular setting, say I'm in epoch 2, I'm minimizing the worst case error over A2. So I have this function G here defined, depending on my design points mu and lambda, which corresponds to the worst element in my design points in A2 and the norm of this worst element, which I'm trying to minimize. So I'm trying to minimize with mu and lambda, this function G, picking my design points to minimize the error in epoch 2. Simple example here, two subspaces, blue and red, two design points only, very simple. A corresponds to 0, 1, 1, B to 0, 1. Question is here, if I sample B one time and I sample A mu times as mu increases, how does the error for B decrease? How will B change as mu goes off to infinity? Both are quite close to each other. So I guess the natural prediction would be that the mean squared error will drop significantly as mu increases. So I have a small plot here, which is this one here. A is the, blue corresponds to the mean squared error of A, which does what I at least expected. It goes down very fast as mu increases. Here on the x-axis, I have the number of samples I use for A. The red curve or red line corresponds to B and the mean squared error of B, which now uses both samples and does this projection onto the subspace. And what you can see here was, for me at least, quite surprising. So 0 improvement in the estimator. So you get a lot of samples here in A, arbitrary many really, and the estimation performance of B does not improve at all. I also have a small proposition to show that. I don't know if I have time for that, but I quickly just want to point out the key ingredient. In the setting, partial orders are actually quite useful. So most of the results I'm stating here just using some simple tricks with partial orders. So what I'm having in mind here are positive semi-definite matrices, which you can order as usual, A smaller than B, if the difference between them is PSD. Important is in this context that if you take inverses, then you reverse the order. A smaller b implies b minus 1 smaller a minus 1. And there's a version of that result for the pseudo-inverse, which I need. If a is smaller than b, then the range of a, which I don't note here, this is Ra, is a subset of the range of b. And I have this property here that if I project onto the range of a times b dagger times the projection onto range of A, since this matrix is smaller than A dagger, if A was smaller than B. So the pseudo-inverse in some way also reverses the order. I actually was interested, I kind of derived this from scratch in 2 pages, but this must be a complete standard result in some engineering book. I looked for a while around to find a reference for that. So if anyone knows a reference, please let me know. So I double checked it. I'm sure this is correct, but I just don't know the good reference for it. So these are quite useful simple results which allow me to prove my first proposition here. I'm comparing the estimator which uses samples from both epochs that corresponds here to the covariance matrix given here. So the one I've shown earlier, weighted linear combination of the outer products of AI and Bj versus the estimator which totally forgets about the samples in epoch 1 and uses this covariance matrix. And then what I can show is if my design points are all linearly independent, some of that can be relaxed, but I need linear independence at least of the elements A1, AD1, and B1, BD2. Then the error Bi at the design points, so this is only for the design points, not for other points. The error at the design points using samples from both epochs is exactly the same error as when I only use the samples from the second epoch. So that's in some way quite disappointing. No improvement whatsoever at the design points by using samples from the first epoch. What this also is saying is that the whole G-optimal design doesn't make any sense in this context. I can place in here potentially a best weighting, best sampling for my epoch 1, but it doesn't really matter. The function G, the maximum norm over my elements in the second experiment is totally unaffected by the design. So the whole G-optimal design doesn't really capture the multitask setup. I have a proof which I'll possibly skip. I don't know if we have later on a chance where I could go through that. It's not too difficult, but I think time-wise I'll just skip this one. And let's move on.
It just alert you have 5 minutes.
So I have also another 3 slides, so I might go through another proof which I have. I think this would take a bit too long, but thanks.
Evan, well, I don't know. Can I ask a quick question? So have you, I think it's kind of like, yeah, you want to have these A vectors in the intersection of the 2 subspaces. And like, if you have that situation, then the A vectors can also have, right? So that's the situation where, I mean, the subspaces have a non-trivial intersection, and then one test can have the other. This is essentially what's happening here. I don't know.
Yeah, it might be. I think some intuition like that, I have that too. Yes, yeah, I think so. Let's quickly move on for the last 3-4 minutes. Take a different example. Sorry, this figure's not particularly cute. So let's have a look. I consider now the subspace corresponding to the span of B and C. I place 1 sample at C, 1 sample at B. I have again my element A, which I will sample mu times. so potentially a lot of times. And I'm now interested in the mean squared error at D. I don't have any points at D, so D is not a design point, but it lies in the span of C and B. So now at least you would hope that the mean squared error at that point is totally dominated by the point closest to it, which is the point A, and that the points at B and C, which are very far from it, don't really have an impact. So at least now we would expect, or I would expect, that the mean squared error decreases significantly with mu as we get more and more samples at A. So I've scribbled down the definitions of these points, but this is secondary. So assume B and C has a single sample, D has no samples, and I'm interested in the mean squared error of D using all the samples, including a lot of samples of A. So this is a plot for it. So the error for A goes down as expected. The error for D is again completely unaffected by the samples in the first epoch. So even so B and C are miles away from D, they totally dominate the estimate of D, completely ignoring any kind of points in A. So I have another proposition which kind of verifies this theoretically. So same setting, I might quickly discuss this proof, which is easy enough. Same setting, so I have linearly independent design points in the first epoch corresponding to A1 to AD1, and points B1 to BD2 corresponding to the design points in epoch 2. All of them are linearly independent. Now I take any element in the span of the second design points, so any element in my subspace U2, and the mean squared error for B using all the samples is exactly the same as the mean squared error for B using only the samples from the second epoch. Main idea of the proof, which I have on some appendix slides, is that the design points are orthogonal in the inner product implied by the C dagger and C tilde dagger covariance. So that is this line here. If I consider AI versus AJ in this induced inner product, then this is equal to 0. If I consider AI and BL under this inner product, then this is equal to 0. And same for BL and BK. So all these elements are, if you like, in the induced inner product orthogonal, which then directly lets me translate my earlier result to this setting. Say B, because it lies in the span of the BI, can be written as a linear combination of these guys. And then I can just open up the two sums. So looking at this element here, substituting in the sums on both sides, moving the sums outside, moving the AIs outside. Because of orthogonality, the cross terms cancel. I get here then a single sum over all the elements in the second epoch with a weighting alpha I squared times BI transposed C dagger BI. Due to my earlier proposition, which I just stated, this is equal to BI transposed C tilde dagger BI. And then I can decompose or recompose these things back together, and I get B transposed C tilde dagger B, which corresponds to the mean squared error. So mean squared error under C is exactly the same as mean squared error under C dagger. So all these samples are totally useless when I'm using the maximum likelihood estimator. Okay, so I just want to summarize quickly. So in this setting, unless the subspaces overlap, in this setting, the naive estimator or maximum likelihood estimator is absolutely useless. I don't gain any benefits from having multiple epochs. The samples are totally wasted. Similarly, the whole traditional designs that you usually consider, G-optimal design, A-optimal design, and so on, are not meaningful. There's nothing to design here if I'm sticking to my naive estimator, which is the one which is underlying classical designs. So then the question is, are there other natural estimators in the setting which can benefit from samples of old epochs? So you would hope so. And are there corresponding interesting designs associated with these estimators? And I just want to stop here and say yes to both. So we have some results on that, but to see these, we'll have to wait, I guess, for our archive paper whenever this will come out. But there's hope, so it's not all lost. The naive estimator is just the wrong choice for these settings. Okay, thank you.
Thank you, Steffen. While the third speaker,
Shall I stop sharing?
Vinay sets up. Yeah, I just had a quick question. So I think you just pointed to the problem and then there's like a teaser. We didn't get the solution. But the idea is the issue that the naive estimator is not thinking about other tasks. Like that's I guess the main issue. And it's just that the samples you would collect without thinking about other tasks are just almost orthogonal to the samples.
So yeah, under this inner product induced by the covariance matrix, they're completely orthogonal, and therefore you don't profit from them. Yes, yes. Yeah. Yeah, for me, it was a bit surprising. I thought in the beginning, for sure, if design points are close by, there must be profit, but yeah. Okay.
I don't mind.
Yes, maybe in the discussion session, you can give us a little bit of overview of how one could handle it.
I'm okay with that.
If you don't mind revealing your secrets before your archive paper
Sure.
is released.
Not that I have all secrets yet, but I can reveal something.
Yeah.
Yes.
Yeah, sure.
Cheers.
All right, thanks. All right, we have our next speaker.